This is the third lecture, and we'll be talking about applications of modular theory in quantum field theory. So let me just start by listing 4 main applications so far, in my opinion, and I will focus on the last 2. So the first application is the average null energy condition. Average null energy condition, yes. / Markov property of vacuum quantum field theory. So the average null energy condition says that any quantum field theory in arbitrary dimension has this positive operator, which is a integral of null component of stress tensor on a null line. The Markov property is much stronger than this, and people use modular theory. Horacio Cassini and collaborators, they use modular theory to prove the Markov property. I'm happy to tell you more about it, but I'm just making a list at this point, so this is not going to be the topic of the talk. The second application is quantum null energy condition. I want to highlight a recent paper of Tom Faulkner, and unfortunately I should have kept track of the references, and a collaborator that used modular theory to prove quantum null energy condition. It's a beautiful paper, very, very complicated, but beautiful, which says that if you take 2 arbitrary states of quantum field theory, take vacuum for simplicity and an excited state, and you do it so this is a region that you take to be a null region for some like Rindler wedge for simplicity. If you do a deformation in a null direction, the second derivative of this guy is positive. So the fact that the first derivative is positive is monotonicity of relative entropy, and the first derivative of relative entropy for this expression is precisely the expectation value of this A-neck operator in psi. So it's a null direction. So let me draw a picture. Here's A, this is A prime. So you make a null deformation of region A, U is this.
And psi and
psi is some excited state. So let's first start with this. Relative entropy, as I make a deformation of the region, the relative entropy, this is the deformation that shrinks the region. So yes, so it's like this. Larger region. No, it makes the region bigger. Sorry. So this deformation makes the region bigger. Therefore, the first derivative of relative entropy has to be 0. You take this to be the vacuum in Rindler wedge, left, right, this setup. You calculate this first derivative, and the answer is this. That has to be positive, which tells you that this operator is positive. Now, monotonicity of relative entropy is a statement that holds in any quantum system. It was proved in modular theory for arbitrary systems, from qubits to quantum field theory. However, quantum null energy condition is a statement of different nature. It says the second derivative is also positive. This is not implied by the monotonicity, and you have to use more tools of modular theory that are specific to quantum field theory. There's a proof of this, it's a recent proof of this in modular theory. So these are the things that I will not talk about, but I wanted to list. This is not true. The things that I'll talk about, I'll focus, are 3 and 4. So we discussed this in the last lecture, that the things that come out of modular theory are naturally connected to information theoretic quantities. As an example, I gave the example of relative entropy, but it's important to have in mind that the relative entropy is the mother function of the so-called asymptotic information theory, meaning that all the measures you have ever heard of that have to do with, let me just use the quotation mark, asymptotic information theory, I can define for you what that is, are one way or another related to relative entropy. That includes mutual information, conditional entropy, conditional mutual information, entanglement entropy, and all such things. It's a master function you cook up all sorts of information theoretic measures from. So, if you could connect this somehow to correlation functions of quantum field theory, then the constraints of modular theory on the relative modular operator would imply constraints on the information theoretic quantities, which would imply constraints on correlation functions. So I'll work out an example of this, which gives you some new inequalities that we don't know how to prove using other methods, at least I don't. They won't be the most exciting inequalities, but at this point it's a proof of principle. So this is going to be part 1 of the talk. In part 2, I will talk about a different application. Okay, so let me yeah, so okay, so let me, I think I'll focus on the argument, a simple argument for the physical picture behind this statement, that this is dense in the Hilbert space. So how you want to use this as an application, I'll comment on at the end. But this is more of a result than. So a generic comment, which is somewhat vague and hand-wavy, is the following. If you go after constraints of quantum field theory that come from, say, these type of deformations. So any deformation that makes the region larger gives you constraint. From just playing around with the inequality and from experience, we have learned, it seems to us, that the constraints are strongest when the deformations are null. This is just an observation we've made. Every time we're doing a deformation, the strongest constraints come from the null deformation. Now, because these are null deformations, every time you put the theory on a lattice with a cutoff, this constraint usually gets obscured. That is why we need to use modular theory to obtain the strongest constraints. At least, this is just an observation. So what are these constraints we're talking about? The constraints that I'll be talking about are results of unitarity and Poincare invariance. There's really nothing else here. Yes?
You said that the first derivative of the simulation matrix relates to the average analysis condition.
Yes.
Because the U kind of shifts and you get a line.
Well, you just do that, calculate that quantity, and you find what's up there.
But what happens if you do a local deformation?
Local. Oh, this is what it is. So this is the null sheet that defines the region. So I'll try to draw a three-dimensional picture. This is X. This is Y, and then this is T. I don't know if this picture shows much. So this is this picture that I'm rotating to see it to look at from the side. This deformation I'm talking about, if this is Rindler wedge, that's defined using this horizon. This horizon is this horizon. I'm doing a small deformation at a point.
Yeah, but it's extending to this other point.
So no, sorry, I should have said that. Sorry, I apologize. So everywhere, then you get positivity of P minus, which we knew about. So you have to extend and do a small deformation at a point to get that. Sorry, I should have. So that's
Supported over a line or not?
no. The deformation is tiny.
Just a point?
At the point, yes. Yes. But the result, the way it changes, this. So the operator is defined everywhere. The operator is supported everywhere. A small deformation in the region changes the operator by that expression, which is an integral over line. Yeah, sorry, I should have said that. This is not, so I'm just being very schematic here. The language I'm using here is looks like two-dimensional. This is a function worth of variations.
Can I understand this from quadratic? That is that, if you change a region, they're really interested in not just that region in space, but its whole causal development.
Yes.
And so if you make a small bump in space, you're really changing over the line, changing the light profile.
Yes, your change is going to be non-local. However, the fact that it's an integral of stress tensor on this line is somewhat complicated.
You kind of without it assume that when one talks about decomposition of the inverse or whatever, the algebra in two regions, A and A prime, where A prime is complement of A, you are always taking this Rindler picture. What is the
No. This is just generic quantum field theory. There might not be an algebra on a constant time slice or anything. This is just.
You need to generalize this formula if you are not. So for the formula, the way you read it, that those equations probably assume that you are quantizing in a constant
No.
place.
No, there is absolutely no assumption. So this operator exists in quantum field theory. In particular, to think about CFTs, there's no assumption when we talk about the spectrum of CFTs. In the spectrum of CFTs, there's this T mu nu as an operator, and you could define that null, that light ray operator, and it's not a statement about a certain quantization. It's a true statement. It's a positive operator. It's an operator statement. It's not basis independent.
The second one, the quantum non-energy condition.
Yes.
Here when you say that I am considering a region A and then I am changing the region by null direction.
Yes.
Here when you say region A, I thought that was, you didn't say but...
No. So here. So there is an algebra here for region A. The second algebra is this region B. These are algebras associated with different regions of space-time.
And in a way, is it right that if you just take a little constant time slice,
Yes.
and you look at the algebra as you define the operator algebra for all operators on that space,
Yes.
you're automatically generating all simple operators that you would get in the full possible development.
So for a free theory,
Because
you
Hamiltonian-
right. So for a free theory, you can talk about the algebra on a constant time slice. For an interacting thing, you have to fatten this up by tiny bit.
Okay, but let's say I do that.
Absolutely.
then automatically generating anything in its course.
Indeed. So here's the thing. So the algebra of this, the von Neumann algebra of this, is equal to the von Neumann algebra of a causal development. So if you can take any region that you want that has this property. So the von Neumann algebra associated with this region is this causal cone.
So really, one way of thinking of it is always think of the causal.
Exactly. You're always thinking about causal, the causal developments.
by the algebra of living in this time-like separated thing?
Time-like
So,
separated.
otherwise,
Sorry, you're thinking of this region?
No, you have these two wedges on the left and the right.
Yes.
With an upper and
Oh, the algebra associated with here. Okay. So, well, we can talk about that. That's not independent of these two. So the information content of the algebra here and the algebra here generate the whole thing, right? That's a different sector. Now, that's a very, very interesting sector, but I'm happy to tell you more about it offline. There's an algebra there, indeed. Okay.
That's very closely related to what Subrat and Giriya was. Because if you think of this in the context of the eternal ADS black hole,
Yes.
that this is one side of the field, this is one outside, that's the other outside, that's the negative.
Right. Right.
They work in the ADS.
So,
And
I can make one comment in 2 dimensions. This maybe this is a good analogy. Take the algebra of this 2 dimensions, right? This is the algebra of an interval defined by using these points, these 2 points. To get that algebra you're talking about, take this point to infinity, or the other one to minus infinity. That's what the algebra is. That's the algebra you obtain. All right. Okay. So. I was saying that these are constraints of unitarity and Poincare invariance, meaning that whatever so if we only use unitarity, yes, no, sure.
When you said this, this fat slice, you said something about this being valid only in 3 things?
So if you take it to be an exact time slice, then there exists an algebra only in free theory, because the field operator and the derivative generate the whole thing. In an interacting theory, you need to really fatten this up by a tiny bit.
that's basically because you will have operator phi and phi square and phi cube and so on as being independent.
Yes, indeed.
You have infinite number of initial conditions.
Indeed. Indeed.
That means it somehow
Gives you enough, because if you just have all derivatives of, you can integrate them all and get a non-local equation for let's say phi.
Yeah.
But still here is fine.
What?
Still here is fine.
So it will just be non-local intact. You need to specify arbitrary number there.
Right, but you want to specify non-linear operators to come out.
Yeah, you specify whole algebra in that. But it's just not enough to specify things at one time.
Yeah. Okay. All right. So these are constraints of unitarity and Poincare invariance. So whatever we find will hold in any quantum field theory in any dimension. I want to comment here on the fact that there is also an assumption of locality. So far we're not making an assumption of locality. By locality I mean being able to define the theory. So what a physicist would mean by locality could be existence of a conserved stress sensor or things like that. I'm not making that assumption yet, or in this talk at all. So unitarity and Poincare invariance. And so keep in mind that the reason we are doing that is that in quantum field theory there are no density matrices, traces, or von Neumann entropies. However, we can still use modular theory to make progress.
But you will assume that operators here and there.
For sure. So the thing that's causality, right? The operators here and here commute. Now, there is a statement called duality often. So if you take the algebra of A and look at the commutant, which is all the operators in the algebra. So first of all, the algebra that both of them generate is phi 1 infinity. It's the algebra of bounded operators in the Hilbert space. So the commutant of the algebra of A is all the operators in here that commute with this. Of course, algebra of A prime is inside this. If they are equal, then you say you have duality. In the presence of charges, you do not have duality. But in the presence of like funky sectors or things like that, you do not have duality. But anyway, so I wasn't planning to comment on this. Good. So let me switch to this side. All right. So let me review a little bit what we talked about last time. So quick review of modular theory. The operator that we care a lot about is called the relative Tomita operator. So in case you're looking at Edwards notes, the notation I use and all the world uses is the opposite of the notation that Edward uses. So he flips the two. That has caused a lot of confusion. But if you keep track of the definition, well, I think this definition is probably most easiest to work with. So A is all the operators in the algebra of region A. Of course, this relative Tomita operator carries the A label. So it's an antilinear, and if this is a Riech-Leiter state, this operation, this equation defines the field, this antilinear. You can close it. You can define the action of this on every vector. Then you look at its polar decomposition. This is called the relative modular operator, relative modular conjugation. But this is what it is just a norm of this guy, the norm of this. All right. So let me draw the picture again. I'll draw this picture 1 million times. So a bunch of comments about this. Delta omega psi, that is this for region A, is positive. Therefore, you could, I'll use this notation, but let me write it once and explain it. It has a polar decomposition. This is a projection operator valued measure. If I had an operator that had a discrete spectrum, this would look like something like this, where this would be a projection and lambda would be an eigenvalue. Now this operator in principle has discrete eigenvectors, has eigenvalues, or has a continuum piece to the spectrum. So the analog of this, when it's a continuum thing, we write this as a measure, an operator, projection operator valued measure. So if you are happy with delta function normalizable vectors, you can think of it this way. Anyway, that was just a comment. So if that's to demystify this notation, in case it looks mysterious to you. So second comment, this is very important in my opinion. There's a lot of arbitrariness in this operator. So there is a choice of a region. There is the choice of two states, two vectors or states. Let's say vectors in the Hilbert space. These are vectors in the Hilbert space. And they don't have to belong to the same sector. So you could choose these two guys from different sectors, super selection sectors of vacuum. You could, this object that I defined up there is just formally well defined, even though these guys are in different sectors, different vacuum of the theory. So I believe a lot of the calculations of entanglement entropy are related to, so entanglement entropy is famously divergent. People talk, when they talk about it, they say it's divergent. There are two things you could do. You could calculate, what two things people do is they subtract the entanglement entropy in an excited state with respect to the vacuum. That's one thing they talk about. That is to be understood as probably some relative entropy of this excited state with respect to the vacuum. Or they do talk about how the entanglement entropy runs under a normalization group or in different vacua of the theory. That is to be understood in this language. So relative entropy allows for vectors of different vacua, comparing different vacua. All right. So third comment, these are the things that I said, but the physical picture. So okay, sorry, you can exponentiate this and you get relative modular flow. It's a one parameter unitary flow. What it does for you is that in the A region, it flows you like the modular flow of omega, and this guy is like the modular flow of psi. So those equations mean the following. So if A, okay, I use this notation. For me, A is always in the algebra of A, and A prime is always in the algebra of. So A is always here, A prime is here. Of course, there are operators that are neither A nor A prime, on which the action of this guy is complicated. So the relative modular flow of this is independent of the state psi. And, sorry? They're both A. So first of all, relative modular flow preserves the region, algebra, the region. So this is inside A. Preserves the algebra. I think there's a sign flip, I forget. Okay, very good. And you could convince yourself this is consistent with the things that you know by working this out in the case of type 1 algebras. This is just sigma tensor rho of rho minus I, so minus 1. So yeah, this is the density matrix of omega. Well, actually, let me use this language. No, that's better. Sorry. So this is the density matrix of region A in omega, and this is the density matrix of region A prime and psi. So now you can see relative modular flow. For example, if I look at this equation, what it tells me is which is, and this is the modular flow of left, and it's independent of psi. Which motivates the following definition. If you take something like this, from these definitions that we have, this looks like, sorry?
This is not the relative.
This is, yeah, so when both of them are the same, this is modular flow, right? So what you do is that you look at this and multiply it by the modular flow of rho with an inverse to cancel this. You get an object that's a unitary that's defined only on the left. This thing is called the cocycle. And one of the important results of modular theory is that this, even when you're not in type 1, is still a unitary flow in the algebra. And you can see why, because all the divergences had to do with the fact that, so near, they all have to do with, with here, but what this operator does is that it flows you back this way and it flows up with delta of psi, and near here they cancel nicely and it smoothly connects. That's why it's well defined. So this cocycle is going to be the hero of the second part of the talk. Omega is some state. There are two different states. So yeah, sorry. Let me clarify this. Let me clarify this. So, for instance, every time I use this notation, hopefully I will not change my notation. And if I look at A prime, that's going to be A, so on and so forth. Okay. So last point that I want to make is the following. Well, I said this just right now. If you take both of the states to be the same, it trivially falls from the definition that this is modular flow. Modular operator. So modular operator, I told you that there's a symmetry associated with it. It's called modular symmetry, which says that the state under this is invariant. What it means is that if you take the algebra and evolve it with this, the expectation values in omega will be invariant. Oh, sorry. So, of course, this acts on the algebra. It acts on the algebra. It's an automorphism. It maps the algebra. It's a linear map that maps the algebra to itself. However, it's an outer automorphism because delta omega does not belong to the algebra. It's non-trivial on an AA prime. So the fact that this is a symmetry, just let me give you an example of why this is the case. What is it? So what an example would be if omega is the vacuum of quantum field theory, we said that this operator is e to minus pi boost. This is just a statement that vacuum is boost invariant. Vacuum actually is the only boost invariant state of quantum field theory. This is going to be important for us. There are no other states in the Hilbert space that have the same modular flow as a vacuum. Now, here's a question. What is a state that is invariant under relative modular flow? This is the state that looks like vacuum on the left and psi on the right. Why is that? Well, we said this before. Oh, okay, maybe I should write it again. No, I'm here. We said this before. The relative modular flow on the left. So, sorry, no. What is nice about this state is that if you look at the relative modular flow in this state, this is invariant, right? Now, if this is in the algebra, we saw that on the left, this is just boost.
Is it totally non-similar at the origin? Even if such a guy exists?
I'm not guaranteed that it exists. It could well be singular. But that's right. So let's say I'm assuming that it does have an eigenvalue. So from the point of view of the algebra, it should be boosting operators on the left. It should be boost invariant. Now vacuum is the only boost invariant state. Therefore, from the point of view of the algebra, this is vacuum. Well, okay, so omega means vacuum, the local state of vacuum. Now, the other side, if I take this to be A prime, relative modular flow, this still has to be invariant because this is invariant under relative modular flow. Then, from the point of view of right, if the modular flow of the state psi was unique, it would look like psi on the right. So I have not described to you why that's true, and in fact, it's not generally true. But this was just some intuition that I wanted to give. So this state, roughly speaking, looks like vacuum on this side and psi on this side, roughly speaking. All right.
Could you write in the definition of omega, delta omega psi? Which one and what?
So in type 1 or?
No, so that on A.
Oh, you want to denote the action of it?
Yes. Oh,
so,
S.
Oh. This?
Yeah, I'm sorry. No, I'm sorry. I wanted the definition of S.
Oh, the S is this. Of course, in the algorithm.
So suppose we choose A to be identity. So
yes.
Then, yes. So then S has to have the property that S of omega psi on psi is equal to chi.
Yes.
So an S that would have this property is something that is psi chi.
Sorry. So so you have this equation. Okay.
So
then
S has to be true for all operators. But if I just wanted this condition for identity, I would get
Yes.
psi chi.
Psi
I
chi.
would get the operator chi, bracket notation. So if I get psi and bra, get psi and bra chi. I want an operator.
So what is chi?
It's omega.
Ah, okay.
Outer product, right? I want an operator.
Yes.
I just was wondering whether that's the same thing you wrote there. That it was.
Well, the action of this on identity is trivial, but the action of it on
But you just reverse those two. That's.
So you want omega psi?
Sorry,
No, sorry. Go ahead.
Not for identity.
Oh no, that's just true for identity.
I know it's true for identity, but I was just wondering whether that was the statement that you made, that it was the operator that the idea, you wanted the opposite.
Yeah.
That wasn't.
So this operator, it does help to write it down. So the operator is this. This is the operator.
That's right.
No, that's fine.
Yeah, that.
So this is what the operator is.
He wanted an operator which, he wanted to know what state.
So I wrote down the relative modular operator. This is what it looks like. So alpha is the basis of psi, and k is the basis of omega, the Schmidt basis of omega.
Right.
Oh, sorry, I think I flipped them. I meant to write this.
And then there's S is that plus other things.
No, it's yeah, that's right.
Plus things that is.
It's multiplied by the following thing. So what is S? So S,
It looks like psi from the right.
so here's what S is. So this has a polar decomposition. I wrote for you what this is.
Yeah.
Now I have to tell you what the relative modular conjugation is. So relative modular conjugation is an anti-linear that in this basis, acts as alpha k, where psi is sum over k, pk, kk, and psi is sum over k, pk, alpha k, alpha k. All right.
Right. No, he was making the statement that S, the state that is identified by S, looks like psi on the left and chi on the right.
So here's one thing that you could do to simplify your life. There is one thing that you could do, which is so you could pick. So you had a local state, which was the restriction of this vector to this. You had a local state for the other guy. Let me write it this way. That's a restriction of the vector to this. Now the choice of vector has an ambiguity in it with a u prime. You could use that ambiguity to define this psi in such a way that this becomes j omega. So that you just, and that thing is called the natural cone. Equation simplify the natural cone. So in the natural cone, so what this equation is true. So if you pick that particular representation of the vector, that's like this, then this is true. So J goes out of the picture.
Okay.
All right. So, maybe I wanted to say this. I already, here was the definition. So let me just write this. So importantly for us, for any B inside A, delta omega psi, the relative modular operator, of B is going to be larger than this. This is the monotonicity equation that's very important for us. This is an operator inequality with any two choice of regions that sit inside each other and any two choice of states. This is an enormous number of inequalities that every quantum filter should satisfy. All right. So now we get to part 1. Are there questions? So what we're going to be doing in part 1 is that we're going to take this, write down an object related to this guy in terms of correlation functions, then use this inequality to derive some inequality for correlation functions. So what is that object? Let me write it down first. So I first give you write down the form of it, because at the first look it looks very, very complicated. But I'll try to explain. Let me write it over here. So take delta omega psi to a power of minus alpha between range minus 1 to 1. Look at, so this is a positive operator, I don't want to mess up with that. Look at the expectation value of this guy in some state phi. Take the logarithm, divide by 1 over psi, 1 over epsilon, and take a supremum over all psi. So it looks very, very complicated, but this is going to become a correlation function. So I'll try to walk you through this.
Phi is any state.
Phi, omega, and psi are any states, really. These are all any states, and they don't even have to be in the same sectors. So this thing is called the sandwiched Renyi divergence. So let me just list it. In the limit of alpha going to 1, this becomes relative entropy. If you take the limit of alpha going to 1, this becomes, so the limit of alpha going to 1 of S alpha is simply minus phi log omega phi. Phi, what I defined to be the relative entropy yesterday. So it's the Renyi family for relative entropy. It has the following two properties popping out of modular theory on this guy. Sorry, say it again. Oh, no, to prove the supremum happens when psi is phi. There's an order here. I think that's true in this case. It's not, no, only at alpha going to 1 that happens. Yeah, the supremum is not easy to take. I'll write for you what the supremum is, well, maybe, depending on how much you want to get into that. But it's in the paper what the supremum is. As alpha goes to 1, the supremum is indeed at that point. So it looks very, very complicated, but I'll try to convince you this is nothing but a correlation function. Well, I mean, in certain cases. So there are two properties that follow from modular theory. One is this. For any alpha larger than beta. Well, I'll actually not use this. Maybe, I said it, but I'll not use it. The other one is this function inherits monotonicity from monotonicity of relative entropy. So, relative modular operator. So this is an operator worth of inequality. I take this to some arbitrary power. Well, not arbitrary, in between minus 1 and 1. And of course, I'm going to have delta omega psi to a power of alpha of A still larger than B alpha. If it's a positive power, if it's negative, you flip it, right? And then when you put a minus sign, you flip this guy, right? Then I'm just putting this inside here. So monotonicity is just goes for the right. This is a way, this is a trick to package this operator monotonicity in terms of correlation functions, correlators. Sorry? Oh, sorry, I think, well, okay. I changed my notation. Sorry. Okay, very good. So to repeat, this is going to be related to correlation functions. And this inequality is going to be constrained on correlation functions. But let me first tell you what the constraints are going to be, because to massage this into correlation functions, there's a whole bunch of a bunch of tricks, and if you lose your interest in the process of going from here to correlation functions, at least you know what the results are. So I'm going to tell you what the constraints are, and then you can judge for yourself. Again, this is a proof of principle. So for me, it was important to get new constraints we didn't know about. It might be the most interesting ones. So one thing to say is that one thing I'm going to do is, which is very unnatural from point of view of modular theory, is I'm going to forcefully go to Euclidean space. So modular theory is naturally formulated in Lorentzian space. It's very nice and neat, and it's Lorentzian. If I do the analog of what I'm doing right now, I could do it in Lorentzian space and I get a whole bunch of inequalities. But somehow our community is more familiar with Euclidean correlators, so I forcefully went to the Euclidean space. So here are the constraints. Maybe people can prove them using other methods. I don't know how yet. So first, let me start with an inequality that you do know already and related to that. So as far as Euclidean correlators go, the only things that we do have, or we believe we have at our disposal, is reflection positivity and analyticity. So this is a Euclidean plane. I'm going to look at a 4-point function of a scalar field. Phi star are arranged this way. If it's self-adjoint, you can get rid of that. The distance between this pair is A. Same thing here. The distance here is 2x. It's a 4-point function, Euclidean space. Sorry, say again? Yeah. Well, dagger is... So what are the properties that it has? It has positivity by reflection positivity, right? So phi star, I'll suppress the locations, is a norm of a state, proportional to the norm of a state, if you pick this as your quantization, and of course it has to be positive. Maybe I want to leave more space. Furthermore, it's monotonic. There's monotonicity. What does it mean? It means that if you take minus del x of phi. Now, let me remind you, minus del x here means separate the two. So this was your quantization line. Minus del x means evolve by Hamiltonian. Because of what I just told you, this is positive. Of course, I can use analyticity, and I know what my Hamiltonian is. I can evolve in a null direction. So there will be some u is some null direction. This is analytic continuation. This is also going to be positive because it will correspond to some p minus, which is a positive operator. This is some analytic continuation of Euclidean correlators. So there is a nice interplay connection between monotonicity and positivity. Positivity is just reflection positivity. Monotonicity here has to do with the positivity of an operator. So this is somewhat already analogous with this setup that I had. I had a positive operator that was also monotonic. So I'm trying, we'll get there, how these are. Well, okay. Well, the connection is a little bit trickier. So one thing to say is that, so what I'm doing is that I'm taking this phi star, and separating them. Of course, as I take them all the way to infinity, they will cluster. But the point is that at So the fact that as I take them all the way to infinity, it will cluster, tells me the following. Tells me this guy over this log is positive. 2. Sorry. And monotonicity tells me that as you vary, as you separate them. So as you take these, so okay. Yeah, this is just a statement that if you separate them all the way to infinity, at each step you're going by a tiny bit. Yes. No, this is just implied by the fact that this is positive. Oh, sorry, I think I misspoke. You're right. I think I misspoke. Yeah, this is just implied by the fact that this guy is positive. But this is a structure that I will use in that equation. That's why I wrote this down. Okay, very, very good. So we had a positivity property and monotonicity property. Now, let me write down the new constraint. So, I wish I had a color, whatever. So, take the same setup, forget about this piece, and actually just take a slice of pizza of the same picture where this is 2 pi over n. So, some slice like this. Rotate this and copy it. Rotate it and copy it. And so on and so forth. So you get the 2 endpoint function. When n is 2, yeah, sure.
If we just do the OP, this is the statement that because it's positive definitely.
Yeah. Just positive definitely, yeah.
It's positive. And then this by positive. Exactly.
So what I get is a 2 endpoint function. This is just a slice of pizza over here, 2 pi over n. Forget about this piece. I'm going to rotate this, copy, rotate, copy, rotate, copy, n times. So I'm going to get a 2 endpoint function. So let me just draw one particular case of it, which is n equal 4. So n equal 2 is what I had here, right? Good. So now what is my correlator? My correlator is in this particular 2 endpoint function. Is it positive? Yes, it is positive because you could still, by reflection positivity, you can draw a line and see that it's positive. Sorry? Oh, n is, well, I want to have one sheet, so yes. This is a general statement for arbitrary positive, and that's the natural number. So, yeah, so, sorry? Yeah, and n equals 3 as well. There's a picture. Let me draw it. So this is n equals 3. Then this is your. Sorry? So this is 5, 5 star, 5, 5 star. This is a n equals 3. It's a 6-point function. Oh, because of this line. Sorry, this is reflection positive. So I'm taking this picture and rotating by 2 pi over n.
What's that 5 stand 5?
Oh, I'm sorry. Yes, sorry. I'm rotating by 2 pi. I'm sorry. Yes. Of course. This, sorry about that. That was a silly mistake. Yeah, of course this has to be like that. Okay. So this guy is reflection positive. Now, is it monotonic? Monotonic in what? You take the slice of pizza and separate this. So you have these pieces. You keep the distance between each pair, but you separate them. So in particular, oh, I forgot to mention one thing here. Let me just say it over here. Not only the first derivative is positive, also minus 1 to a power of n, del x to a power of n, or del u to a power of n, of this correlator is also positive, because that's just h to a power of n. H is a positive operator, so is h to the power. So all the derivatives, so the derivatives are alternating signs. Okay, so I know a lot about that function. So now, is this true? Is this two-on point function monotonic? To my knowledge, I don't know how to use, until now, I do not know how to use reflection positivity to prove this. However, using a zero-relative modular operator, quantum information theory, modular theory, this is followed. So modular theory proves this for you. This is not the scaling, because so I keep these are fixed, so you can think of them as these are fixed, and I move them away. It's not the scaling. The scaling would rescale that. So it's very helpful to think about the case of, as a challenge, it's helpful to use the reflection positivity or all the things that we do know to prove that it's true for 6-point function. It's hard. I don't know how to do it. And also modular theory tells you that del u of this is positive.
Meaning that the correlation function gets bigger as the thing goes closer.
Yes, yes. So here's a conjecture. So a conjecture is that the second del u derivative of this two-point function, this two-on-point function is also positive. This is not implied by modular theory. This would be a generalization of quantum null energy condition, QNEC. We do not know the status of this, but in all the examples I worked out, this is true. So this is a challenge to prove. Now that there is a proof of QNEC, maybe there's a proof of this as well. I do not know the status of this. And higher derivatives is just simply incorrect. You can construct counterexamples. So the positivity of this guy is not going to be positivity of some obvious operator that's positive that you're taking to other powers. The nature of this side and this side are very different.
But how about that inequality working with some symmetric product theory on cone?
Symmetric product theory on cone. This is a one-sheeted correlator.
Yeah, but you can work with TPM.
This is quantum field theory as well. It's not CFT.
Yeah. But you will work with that quantum field P and take n from product on cone and work with some. It's not immediately.
Yeah, maybe there's a way to prove it. Maybe there's a way to prove it, but modular theory proves it for you in one shot. I actually believe if the statement that reflection, positivity, and analyticity are sufficient for all the constraints that there is, this should be provable. So one comment I want to make is that we're not claiming, when I say new constraints, I'm not claiming that this is not going to be provable using Euclidean methods. What I'm trying to say is that this is a new angle that gets certain things that were hard to prove easily. And some things that were easy to prove might be extremely hard in this language. This is a complementary picture. This is all I'm trying to say.
In case of bootstraps, this is more general, but can I just restrict to conformal theories?
Yes.
What kind of constants does this conformal bootstrap?
I tried to get it and I could not. This is a very interesting question. I tried to write this down in conformal bootstrap because these are higher point functions. There are infinite sums over all sorts of OP coefficients, and it's wild. I don't know. I don't know what to say about it. There's nothing simple that I could get out of this. It would be anything you could do would be very interesting because this remains a challenge a year after I wrote it down. But I want to say that what I did was that I wrote down the simplest thing I could write down. This is, okay, anyway, you'll see that in a second. And the conjecture is also potentially interesting. I'll leave this. The conjecture will have to use the fact that quantum field theory is a type 3 algebra, because Koenig used that. Koenig is only true for Poincare invariant systems, and this is probably going to be only true. You have to use the fact that it's only true in Poincare invariant theories.
You also want to believe this for higher derivative X?
So there is something called quantum dominant energy condition, where the second derivative in X is positive. The status of that is not known. I think by observation tell you that usually null constraints are the hardest one, the most general, but I don't know what the status of that is. The higher derivatives are just incorrect. In free theory, you construct explicit examples where this is not true. Yeah, here. Yes. So those. There's no sign, fixed sign. So, sorry, are you asking that whether there exists a del x to the power of n here? No, you can construct counterexamples where it switches sign. The counterexamples are in the paper.
So you do the first thing, generalized free field theory.
Yes.
And check that it is.
Yeah, you do that. You do that, it's true. And you can test this in all sorts of funky theories where we do have access to 6-point functions. It's also true. Often it passes because of some sort of weird reason. So I checked this in, let's see. The example that I wrote down explicitly was free field theory, and you just beat it up. You take any two states, you just beat this up. Then we looked at these, somehow there are these monster theories, or sorry, not extreme CFTs that people somehow have access to 6-point functions. We checked it for those theories, it was correct. You could do this for, I think for generalized free fields is another thing you could do, but that's sort of not the most interesting thing. You could try to see whether it's holographically related to something. I don't know, I have not really explored this much. But I would love it if somebody finds a proof.
But let me ask, vaguely, if these things are, suppose I looked at your inequality and things go very far away.
Yes.
When these two together, it's natural to use the OPE for those.
Yes.
So it sounds like a statement about the positivity about some, endpoint functions are closely related.
Right.
So in particular for your 6 things, it's like a positivity of some 3-point function.
Yes, it looks like at a certain regime, it's a positivity of some 3-point function, indeed.
And it's a 3-point function. No, just a 3-point function of the leading operator you get.
Yeah, because
and that leading operator is presumably, because I'm taking each of these two and replacing it by one.
Oh no, I think this is not true. Sorry. It's not a positivity of a 3-point function, because the identity piece, I can't throw it out. In the limit you're talking about, it's dominated by the identity piece. So I cannot do such a simple argument.
It's 2-point function, these two squeeze to identity,
yes,
and then the 2-point function.
Correct.
First, the unity should make the identity operator.
Correct.
Coming in all
Correct.
Yeah.
Yes.
And the next leading would be 2 non-trivial operators, the rest identity operators.
Right.
And the 2 non-trivial operators would make the square.
Right.
Yes.
Square.
Yeah.
And that's positive.
That's positive. That's right. So good.
No, but the thing is, this positivity has to do with, so there are functions that are going to sit there as you do this contraction, these OP contractions. Yes, kinematic functions. You're taking derivative with respect to those functions.
No, but once you have identity, there is no kinematic function there.
The identity piece does, yeah. In this, what I'm trying to say is that, okay, so you're taking a limit.
That's what the other two guys.
So you're trying to work this out in a CFT, right? In the CFT case, one thing I tried was that I tried to take these guys to be very, very close to each other, and generically I find that this inequality is not helpful because it's dominated by the identity piece. So I can't get a constraint on OP coefficients.
No, but let me just go
Yeah.
through this argument. So you have tier 2 operators.
Correct.
N pairs.
Yes.
Now
Take it 6 of them. The first.
Yeah, okay. So now take them very far.
Yes.
The first thing, let's say you want to construct the cluster decompose ratio with the cluster decompose pair.
Yes.
So the leading is going to be the cluster decompose pair.
Yes.
Where you have identity operator and the channel.
Yes.
Right, now let's look at the correction. You want to show that the correction is positive. Right,
No, the correction is not positive. The whole thing is, the derivative of the whole thing is positive.
Yeah, but
It's not that there's a derivative in there. It's not that the first term that it has to it's not positive in variation of this distance.
No, but he's saying it's positive as in bringing it together, closer together.
Yes.
As you decrease x, the whole coordinator should decrease.
Yes.
So the contribution, there is one term that is independent of x.
Yes.
Which is
yeah, so in confounding theory, instead of taking those very far, you can scale x also.
Yeah, that's the same thing. Yes.
So now that's why I'm expanding in x. That's why
Sure.
I'm expanding.
So here. So 1 pair, 2 pair, 3 pairs, right?
this x was this.
So x is this distance. This is x.
Yeah. So that's why, very far away, you just have identity contributions.
Correct.
Each of them.
So it's gonna be
This connection will be just a 2 point.
it's a 2-point function, right?
Manifestly called.
All three pairs.
No, you say squeeze all but 2 to identity.
All but 2 to identity.
And then squeeze the other 2 to the first non.
Actually, maybe I can say it this way. Maybe I can say, sorry. I can take one more step that's helpful.
That's the same operator.
One thing that I can,
Equation squared, but there's a block. There's a block there.
It's just a 2 point.
No, 4 point.
sorry. Maybe this comment helps. So, first of all, I'm doing a derivative in each pair going away. That derivative is n times the setup where everything is fixed, 1 pair is going away. Right? That's the first thing. So the thing that if you want to say what is positive, the thing that has to be positive is this thing. This is fixed, this is fixed. This pair is moving this way. So this has to be negative, sorry. Yes. So this pair is coming close. This is the thing that has to be positive. Derivative with respect to this x. So I think you can write it down, and it would be great if you could get something out of it. I couldn't.
I have just one more question. So let's take the second equation where you are differentiating the
Yes?
and any different conformity. So let's take this pair of operators close together.
Yes.
So your OP has leading contribution identity and then some operator from every pair.
Yes.
Let's say. Now the contribution in which all the identity operators are taken.
Yes.
That contribution is independent of you. So the derivative
Sure.
with respect to you will kill that. The contribution in which you have identity from every pair.
Sorry, the contribution is independent of you? No, it's not independent of you. So there's one, no, it's not independent of you. Because these identity, okay, so let's talk about this offline, because I'm sure of what I'm saying. I would love it if we can get something out of this. It would be great. We tried and couldn't.
Why the equation that you have on the left is like almost like an ANX on ANX.
I'll tell you in a second. Yeah, it is indeed very much like ANEC. This is indeed, actually, sorry, this is implied by ANEC. It's implied by ANEC. Well, this is positive P minus. If you did your deformation in a tiny bit, is, yeah, sure. All right, so now let me define the following quantity. Maybe I want to keep this, yeah. So the quantity I'm going to define is the following thing. 1 over n minus 1 logarithm of this 2 endpoint function I wrote down. I'm not going to write down the locations. Over the 2-point functions to the power of n. This is a quantity. And this is going to become exactly, oh, okay, I used the board poorly. This becomes exactly that quantity from relative modular operator that I was constructing. So, but let's see how it works. So, to argue for this, I can use modular theory, but it's very fancy language and you probably will not get much out of it unless you have a lot of experience playing with the modular operator. I'm going to use density matrices to motivate it. Euclidean density matrices. So what is this slice of pizza that's 2 pi over? So take Euclidean path integral. This is the vacuum of quantum field theory. And I'm going to perform a path integral around the whole thing. This is going to be, so the vacuum of quantum field theory is here. This is the bra. I'm performing a partial trace over here. The path integral as I go around this becomes sigma of A. The reduced density matrix of the vacuum and this region. This is how a lot of these cutoff dependent calculations are done. So again, I'm using this language because the modular theory language is a little bit cumbersome. But you could do it. There's no problem. Okay, now take an excited state. This is still region A. Take an excited state that is created by the insertion of some operator, distance A this way and X this way. This is a state psi. Psi? They call it psi? Yeah, I guess psi. And then this is the state psi dagger. We'll have, oh, sorry, A over 2. Is it 2A or A? Whatever, so A. This is phi star. So if you construct rho of A, you're going to get trace of A bar psi psi, which is like this, path integral. So if I want to know what this is, this slice, call this operator X, this path integral, this operator that the path integral is equal to. If I multiply this by a power of the vacuum density matrix on the left and a power of density matrix on the right, which is the power is n minus 1 over 2n, n minus 1 over 2n. Remember, this is 2 pi over n. I'm going to get rho. Right? Oops. Therefore, this operator is, X is rho sigma 1 minus n over 2n, 1 minus n over 2n. So what I did over there in my 2n point function was that I was sewing n copies of this together. So that thing is going to be trace of x to the power of n. That thing is nothing but trace of sigma 1 minus n 2n rho 1 minus n 2n to the power of n. All right. So this now is the following correlation function. That 2n point function that I wrote down, and you have to normalize by the states n. That one-sheeted correlator is this. One comment I want to make. Oh, okay. So sorry. So now this guy has a name. Well, sorry. For any two density matrices, you could define the following Renyi family, which is exactly what I just wrote above. Trace of sigma 1 minus n 2n rho sigma 1 minus n 2n to the power of n. This is called the n in half to infinity. This is called sandwiched Renyi divergence because this is just a particular instance of the modular theory expression with the supremum, specifically calculated for density matrices. But I'll show you that in a second. So as I said before, well, you can check this explicitly in the limit of n going to 1. This is a relative entropy. There's another nice limit n going to half. This is called fidelity, but if that doesn't mean much to you, it doesn't matter. Modular theory was used to prove that this is monotonic. Monotonic in what? Monotonic in region size. What is region size? Region size is, if you look at the smaller region, that's changing x. That's why I'm taking derivatives with respect to x. Now, if I move the endpoint of this in a null direction, that's like analytically continuing x in null direction. All right, so one important comment, as opposed to the replica trick of entanglement theory that people use where there are divergences all over the place, this thing is a one-sheeted correlation function. It's UV finite. Therefore, it has a good chance of existence in modular theory. So I'm reversing the logic. Of course, yeah. So, but it's a correlation function that you're taking the limit of n going to 1. So it's very, very clean. No divergences whatsoever. So this, yeah, that's an important point. Okay, so how do I go between this and the other expression? Do the following change of variables. Alpha is 1 minus 1 over n. Ah, there we go. This is lucky. This is lucky. All right. So if you do this change of variables, that expression should become this expression. What do you need to know? Well, you need to know this fact. You need to know that because I use the density matrix language, this is true. Rho. Sorry. And you need to know, sorry, I said rho, no, psi. You need to know one last thing, which is this expression, this is a norm. This is a p-norm. So a p-norm of an operator x is trace of x to the power of p to the power of 1 over p. And then there's Holder's inequality that says this p-norm, if 1 over p plus 1 over q is 1, this is the supremum over trace of c equal 1 of trace of c to the power of 1 over q x. This is how you trade the norm with the supremum. This is a trivial example of this is when it's just 2 norm. The 2 norm of a vector is the supremum over phi psi of all phi's in the Hilbert space. This is a generalization of that. So this is how you get out of this expression a supremum. So yeah, these 3 things, you massage it as basic algebra, and what comes out is this expression. So from modular theory, monotonic modular, relative modular operator told us that this guy is monotonic. Therefore, that guy is going to be monotonic. Therefore, the correlation function equality that I told you about is going to be monotonic. So I would love to derive this using other methods. And I really stress that because it would help me find the next non-trivial example. All right, so this is the end of part 1. I think, what time is it? How much time do I have? Part 2 is going to be pretty short, actually. Okay, so I can wrap it up faster. Yeah. All right, so are there questions? This is the simplest thing I could do, which was take a scale, to relate it to correlation functions. The analogy that I have is that in the past people used causality type arguments to argue that certain terms and certain coefficients in effective field theory should have fixed signs. And in particular, the del phi 4 term in effective field theory should have a fixed sign. This is a causality argument, and people tried really hard, as far as I'm told, to derive this using reflection positivity and analyticity. They couldn't, not that it can't be done, it's just because it's a different angle. So I view it that way. And it would be really helpful if we could actually derive this using the reflection positivity. Sorry? So that's the first step, but what is actually funny is that this language is more naturally done in Lorentzian. So I should just write down more and more inequalities, but I was not expecting to get something that was not known before. So yeah, so hopefully this is a larger program. But remember that I took one of them for simplicity to be vacuum. The other guy, I took it to be very simple state, right? I took it to be a scalar field, the most trivial things I could do. That supremum thing was kind of magical, I admit. All right, I wanted to say one switch. All right, in part 2, just want to, in the very few minutes, because I don't want to bore you guys too much, I just want to tell you a little bit about this other result that I find to be very fascinating. That any two states of quantum field theory could be related using unitaries and a region and a complement. So the proof of this is rather formal. In one of the papers I mentioned, the proof of this was simple, well, explained in simple terms for physicists. However, it's still non-constructive. The proof of this uses Zorn's lemma, which is axiom of choice. So it's pretty complicated, and it's non-constructive. However, well, what is this statement? The statement is this. Sorry, let me write down what the statement is. The statement is for all psi and omega, any two states, and any epsilon larger than 0, there exists u and u prime, u and a prime unitaries such that u prime of omega minus psi is less than epsilon. So this is a Hilbert space norm. If you allow me to use a weaker norm, which is more physical, which is which is an overlap kind of thing, I can argue for this very simply using modular theory, and I can even tell you what that u is.
On the lattice, this is all constraint.
It's incorrect. On a lattice, it's not true. If I pick two states that have different Schmidt coefficients, there's no way you could relate these two states using unitary. This just says that these unitaries do not change the eigenvalues. This says that there are eigenvalues. That was the statement, right? Importantly, this is incorrect in a lattice.
Because this is not dense.
Yes, yeah, exactly. That's exactly the point. Or when the spectrum is continuum, the system is ergodic. This is the whole thing. So I'll explain in a second. So I want to do something simpler, which is the following. I want to argue for you in very simple terms that there exists a state. So let's talk about this locally. So I want to turn this around and argue for something like this, which is a result of that. Take a region of space and an algebra here, and the local state here, which is this. So we're going to take two local states.
You said this doesn't change entanglement, as you said. This doesn't change entanglement, so states with different entanglement.
Correct. Any of the Rennies.
Well-defined there.
Correct. Any of the Rennies, we will not change that. So these are two local states. The weak version I will be talking about is this. For all A, for instance, there's a stronger version. There exists a U in the algebra, unitary, such that U dagger minus A or psi A is less than epsilon at any epsilon. So this is a weak norm. This is a weaker result than the strong one. And this I can easily argue for. And not only I can argue for, I can tell you what this U is. The U is the cocycle. It's simply the cocycle we wrote down. as the only unitary the modular theory defines on a region. And that's the cocycle. So how does it work?
The Rischlinger theorem allows you to use non-unitary operators but on only one side.
Correct.
Yeah, if you use unitaries on both sides.
Correct. Yes, but using non-local operators, you can create all sorts of excitations away.
Non-unitary.
Non-unitary, yes. Using
You can get any
entanglement.
state with a non-unitary operator on one side.
Yeah.
And you can get any state using unitary operators but localized independently.
Correct, correct. All right, so what is the U that does this? The U that does this, remember I defined for you this operator, the one parameter unitary called the cocycle, Cohn cocycle. Alan Cohn is famous. One of the reasons Alan Cohn is famous, one of the main reasons is that he used defined the cocycle and used it to prove a bunch of results. In particular, he proved that this is inside the algebra. Okay? So, all right. Let me remind you what this object is. Oh, sorry, I should have said this. So, this statement has to do with the fact that unitary is the limit of t going to infinity of u of omega psi t. That I'll just, from now on, refer to as u. So, how does this work? Now, let me first write a quick statement here. Say you are in finite quantum systems, you are in state psi, and you look at the expectation value of an operator, and you apply delta omega it minus it here. Pick omega to be vacuum. It doesn't matter because if any state could be brought arbitrarily close to a vacuum, any two states could be brought arbitrarily close to each other. So I can freely choose this guy to be the vacuum.
The action of ut was move with rho upstairs and then move with sigma downstairs.
Correct. Yeah.
T is infinity, basically you're moving to infinity.
So I'm moving infinitely up and coming back down. So look at this guy. We're going to take the limit of t going to infinity. Let's assume first that there are eigenvalues. This operator has eigenvalues. Then this is the limit of t going to infinity of omega prime of e to the power of it omega minus omega prime a omega. Now, there is the Riemann-Lebesgue lemma that says any integrable function, any L1 function, this is an infinite Fourier mode. Any integrable function cannot have an infinite Fourier mode. So this limit will be 0. You could, yeah. Yeah, there are simpler examples than this, but given the amount of time you have, I think, good. So, so that's true if omega is not equal to omega prime. So as you take the limit, you diagonalize the thing. So this limit will give you the diagonal piece. However, if this operator has no eigenvalues, what this limit gives you is just the invariant state of omega. So if the operator doesn't have eigenvalues, this limit gets you only the invariant state, which is vacuum. Right? So now, what did we do? But what does this say? It says take an arbitrary state boosted by infinite amount. It looks like vacuum locally. Of course it does. That's what it says, right? This is boost. You take any operator and boost it to infinity, the overlap of anything local becomes vacuum. But yeah, I don't. There's a trick. The trick is the following. So here's a bunch of equalities that you could check for yourself. and I'm just going to write it. So this is what we are looking at. Sorry?
The notation of IP and what does it really mean? Is it like e to the power some positive numbers times Hamiltonian roughly?
No, this is just boost. This is infinite boost. This is infinite boost.
Infinite boost, but with an I or without an I?
No, this is infinite boost. Boost is real space. This is Poincare invariance, right? This is infinite boost. So, oh, I should have used this better again. So, this is what we're after. So, what is the difference between this and what I want to achieve? This is an operator that's supported on AA prime. I want an operator that's unitary on left times a unitary on right. Correct? So first put in this in here. The state is invariant under its modular flow. I can just insert it. Then there is this beautiful property of the cocycle that tells you that this splits to the cocycle of omega psi times the cocycle of psi omega. Well, let me write this omega psi prime. So this splits into a cocycle on the left and a cocycle on the right. This is just like, you can play with the modular theory to a bunch of equalities from modular theory that are non-trivial, that I haven't told you about. So here are your U and U prime and A. So, yeah, you accomplished what you wanted. You basically took the limit, the weak limit of some UU prime and did this. Now, if you pick your A to be in the local algebra, this U and U prime cancel each other. You obtain exactly what I wrote. That. Where this is the cocycle. Now, what does this tell you? It tells you the following. It tells you that take an arbitrary state and just split space-time into a bunch of disjoint regions that the unit of which is the whole thing. You could act locally here to make the state vacuum. You could copy vacuum here. You could copy vacuum here. You could copy vacuum here. So what you could do is that you could copy vacuum everywhere without touching the entanglement structure. So you get the skeleton of the entanglement structure of the state out by using local unitaries that you do know explicitly what they are. So this is the note I wanted to end with. This is an application of modular theory, because if you're interested in the entanglement structure of these systems, the local state should not matter. And this exactly tells you how to trivialize the local state, maintaining the structure of entanglement, multi-partite, single-partite, however you wish to compute. So this is the second application.
And then that structure would then be the unitary?
Sorry?
That structure then would be the unitary that you use?
Yeah. So the unitary does not change the entanglement structure. So I just use the fact that what I'm interested in is invariant under local unitaries to pick a careful choice of the local unitary to trivialize every local state. I can take your favorite theory of n=4 Mills and make it locally in all patches to look like C=1 free bosons. Now the cocycle for that is wacky, but I can make it locally vacuum.
So once you've chosen your partitioning of your space into regions.
Yes.
And different partitioning will happen.
Oh, absolutely. This will preserve the entanglement structure across these guys.
But if I now partition differently,
it will change.
Different.
Absolutely.
So it's that complicated interplay that makes the
absolutely. Yes, correct. One last comment is that it's certain, almost certain, that the cocycle in the limit of t going to infinity will make this, because it has to patch two states of different energy. it will make this in what's it called? Some sort of a wall that as you take t going to infinity, it will degenerate to a shock.
Fire.
It will make a shock. It will make a shock. Okay, that's all. Thank you.
So Gopal, questions?
No questions.